Okay, so welcome everybody. My name is Enrique Fernandez Serra, and what you're going to see is a mind control room. First of all, I want to do the demonstration first. So I wanted to show you this application that is the control panel, which is the one application used in this project. In this application, the user is allowed to manage the brainwaves generated and read them by the headset that I'm using. Here we can see the sensor location. The green ones are the sensors that are working now, and the black one is the diet sensor. Here we have Expressive Suite, one part of the control panel that shows the user a robot face that is copying the facial expressions doing by the user. As you can see, when I'm looking left or looking right or blinking or even smiling. Okay, not every time, but it tries to do. Okay, the most important part of control panel is Cognitive Suite, because here the user is allowed to record brainwaves and attach the recorded brainwaves to some actions. In this case, push and pull. So every time the user is thinking about the same thing or generating the same brainwaves, the application understands that the user is thinking about pushing or pulling. In this case, when I'm closing my eyes and trying to concentrate, the 3D cube is moving forward or backwards. Then, the application done in this project. For hitting the drum. The application can be also controlled by the keyboard in order to have safety measures, because the application, the headset precision is not as high as it needs to be. Then, returning to the presentation. First of all, we're going to see a little content table of the presentation. First, we're going to talk about a problem, and then we're going to set some goals in order to resolve the problem or improve the actual situation. After that, a little bit of neuroscience is going to be introduced in order to understand the demonstration part scene and some other parts of this project. Then, the material used in this project is going to be introduced, and after that, the main core of this project, the brain-computer interface, which has an application interface and a software development kit. Since ever, there has been people with physical injuries, mobile disabilities as quadriplegia, that can be translated into a very hard situation to deal with. That situation usually involves daily life problems, not only for the people with disabilities, but also for third parties like hospitals and families. So this project began with the idea of creating an application that allows the user to communicate without any physical interactions, using a low-cost neural headset and trying to create a media impact. The main technical goal of this project was the creation of an application that receives data from an external device and transforms them in order to generate an external data to control some device, in this case, it's a drone. In this project, 4 different headsets were going to be compared. In the end, only 2 of them arrived on time. Here we can see OpenBCI, which is a low-cost headset that is fully 3D printable, what means that the sensor can be placed wherever you want in the head. This device is more orientated to some research and investigation. Then we have NeuroSky, that we have here. I have another one here, but they use the same technology, which are 2 dry sensors, one in the front and one in the ear, if you want to see it. Instead of the 14 sensors that Emotiv Epoch uses. This is the Emotiv Epoch, which has 14 wet sensors, and the compulsory wet sensor condition and the difficult positioning of the sensors in the head made not the best headset for this project. For that reason, Emotiv Insight was expected to arrive on time, as it has 8 dry sensors and an easy wear design. But it didn't, so in the end, Emotiv Epoch was chosen for this project. Here we can see what a full sensor map looks like, orientated for hospitals, and the Emotiv Epoch 1, which has only 14 sensors around the head, instead of the 100 that has the other. We can expect a difference between both electroencephalography's precision and device cost. To get a basic idea of the meaning of brainwaves translated into affective states of the user, some study has been done. Alpha waves are more related to relaxation, learning, and meditation. Then we have beta waves, more related to concentration, anxiety, and some levels of anxiety. Then we have theta waves related to REM sleep, deep meditation and trance, and delta waves more related to deep trance and dreamless sleep. These brainwaves are get by dividing the brainwaves of the 14 sensors by frequency. Here we have what the 14 sensor cut from the Emotiv looks like. And we're going to talk again about control panel, which is the Emotiv application panel. Then, the material used in this project is an AirTron 2.0 because of the wide user numbers and the wide information available through the internet. Emotiv Epoch, that has been explained before, and Unity 3D, which is one of the most used graphic motors nowadays. Excuse me. Because of the easy plugin and language integration as C#, JavaScript, or Unity Editor. Then the application interface. The application in this project was made to receive some raw data from the Emotiv headset, get processed by the drivers, in this case EmonJoin drivers, and in order to get control parameters that are going to be sent to the drone. Emotiv Software Development Kit has written functions in order to get those variables, affective, expressive, and cognitive, that are processed by EmonJoin, that receive the raw brainwaves from the headset. To understand how the EmonJoin, the Emotiv drivers, works, a signal processing with MATLAB has been done. The program made records the 14 brainwaves of the headset for 10 seconds at 128 Hz and stores them into an array to have a reference sampling that is going to be attached to an action. Then a second sampling is going to be recorded and attached to an auxiliary array. Both samplings are going to be compared in order to obtain the sampling error between both brainwaves. The average of that sampling error will get the mean error of the comparison. In order to obtain a cognitive state, a filter with a Schmidt trigger has been done in the mean error using two thresholds that needs a small error to get from 0 to 1 the cognitive state and maintains the cognitive state until the error is big enough. Then this cognitive state is going to be translated into a drone's input. Here we can see the reference sampling using this project and the actual sampling. Both are going to be compared to obtain the sampling error. The average of that sampling error is going to be translated here as the main error of the brainwaves. In order to obtain the cognitive state, we are filtering this with a Schmidt trigger. That's the whole plot, but zooming a little bit, we can see better the situation. We have here the drone's input, which is switching from 0 to 1 when the error is crossing the red line, which is plus minus 2 microvolts, and maintains the error, the drone's input until the error is crossing the blue line, which is plus minus 5 microvolts. The drone's input value corresponds to a proportional angle of the drone. In this case, the proportional maximal angle of the drone is 15 degrees. This is how the human child works to understand the thoughts of the user. As explained before, the application is a brain-computer interface that creates a connection between a headset and the application in order to process data and control a drone. Here we can see the application user interface that has been built. To use this application is easy for a user, as it only has to turn on the headset, put it in your head, turn on the drone, connect the laptop with the drone's Wi-Fi, and then just click the connection button. Okay, through this project there has been some problems that can be divided into two different types. The first one were the programming problems that were mostly of them related to the use of the Emotiv Unity 3D libraries. As the Emotiv Unity 3D libraries were different than the common ones which were used in this project. But the most relevant problem here was the function to load the user profile, because it didn't work and I needed to convert the user profile into a byte array in order to load the user. Then we have logistic problems with the device availability. As said before, we were expecting OpenBCI, which we expect to get some more comparison between headsets and to do some research. And the Emotiv Insight, which we expect because of the dye sensors and the possibility to do an Android application, which was the original idea of this project. In the end, it didn't arrive on time, so the application was made only for Windows. In conclusion, even with the headset low precision, the drone's control application worked better than expected. Even that the problems had through the project. The use of this headset can be used for a biomedical project, more oriented to investigation maybe. But even that, the use of brain-computer interface technology needs to be improved a lot before getting a real use, a real engineering use. Okay, here I have added a testing video in case the demo didn't work. I'm not really sure if the demo was a good proof of this project. So maybe I should start a video. Well, I have to say that this test was nicer than the first one, because after taking off the drone, flight straight until it hit a table like it had happened in the demo. The application can be controlled also by the cognitive suite panel, as explained before, that can attach some thoughts to connections. But the most easy way to control the drone is using special expressions and effective states, because every user can use the same headset and don't need to train to get a better result. Thank you all for listening.